All right, clip number 2 for section 1 on lines and segments that intersect with circles. At this point, we're going to be focusing on one of those intersection types, which is what we call a tangent. Tangent, again, the one requirement is that it's going to be some line that touches at exactly one spot on that circle. What the twist is here with this part is that now I have multiple circles. And when we talk about common tangents, we have far more strict requirements where, like, okay, it can only touch one circle at one spot, but if it also has to touch the circle at another spot, there are going to be far fewer options with that. In any given circle, there are an infinite number of tangents I could just spin around that circle. But as soon as I have to limit it with other circles, there are going to be far fewer options. So let's just talk through a couple of those situations. In this first example where I have the Venn diagram, in this case, when I have two intersection points, there are going to be exactly two common tangents. And in this case, if you were to think this, again, like if I were to set this on a table like this, there's one of the common tangents. It's just one that attaches to both on the bottom, kind of like tracks on a tank or something like that, all right? And if this is one of the common tangents, that means on top, there also has to be a common tangent. So anytime I see this Venn diagram situation, there are going to be two common tangents, one on top, one on bottom. Any other twist, it's going to completely miss one of the circles, depending on which circle I'm doing a tangent on. Okay, so there's one on top, one on bottom. All right, now what happens if I have a single point of intersection? Well, I've actually drawn the only common tangent that exists in both cases. Wherever those two circles share that point of intersection, that's where the line of tangency has to be. Okay? Whether they're side by side like this or one within the other, that common tangent, the only place it can touch both at once is where they both touch each other at once. Okay? So if you want to write in parentheses, if I have a Venn diagram or 2 points of intersection between two circles, there are two common tangents. If I have one point of intersection or one common point between the two circles, there is one common tangent. This is where things will start to get interesting, right? Now what happens if I have no points of intersection? In other words, these circles don't touch each other at all, whether they completely miss each other outside of each other, or if they're concentric, like these two, like in this little bullseye looking thing. Let me talk about this one first, the bullseye looking thing. In this case, there are no common tangents. If I were to think in terms of this larger circle on the outside and all the tangents that can exist there, they'll completely miss the smaller circle on the inside. So it can't touch it, it can't be tangent. Whereas if I were to think about all the tangents for the smaller circle on the inside, it'll completely pass through the larger circle, touching it twice, thus not being tangent, but secant. So in this case, the bullseye case, or the concentric circle case, there are no common tangents. Things get a little weird when I have two circles completely separate from each other. So for this, I'm actually going to refer to what I have here in the margin. And I'll show you the solution sheet, which is uploaded now on Google Classroom if you want to take a look. But I'll show you the solution sheet for what happens when I have two separate circles. There are actually going to be 4 common tangents. So let me show you that really briefly. There we go. So this is that other margin example where this is the type of thing that you would see in big ideas. They'd give you a couple of circles and they'd be like, all right, identify the number of common tangents or draw them, whatever it might be. Here's the bullseye. There are no common tangents between those guys. Again, there's nothing that I can have tangent to both at once in this case. Here's one where they share a single point of intersection. There's exactly one tangent line at that exact point where they happen to touch. Anything else would pass through the larger circle at 2 spots or completely miss the smaller circle. In this case, here's the drawn common tangents between the two. Similar to the Venn diagram, I have kind of like the rail on the bottom, if I want to think of it like tracks on a vehicle, or the rail on the top. Again, think about tracks on a vehicle, right? In both cases, those blue lines are tangent to both circles at once. Where it gets a little weird when they're completely separate is I can actually do a tangent that passes in between them. Okay, as you can see, both these orange common tangents both touch the circles at exactly one spot. It's just that it also passes between the two. So you can make that x. And that happens with any pair of circles if they're separated, as long as they're on the same plane. So three-dimensionally speaking, if they're on the same paper, then you can do this kind of thing. But so if you have two separated circles, there are exactly 4 common tangents as drawn here. You'd be able to create an x between them, and you'd have like a rail on top and a rail on bottom. Okay, again, not super critical in this section. It just is more of like a kind of a puzzling thing about how can I create a line of tangent that touches multiple circles at the same time. Okay, back to the notes. Now we're going to talk about the 2 theorems that we're going to have in this section. There are only 2, and this first one is very critical. The tangent line to circle theorem. I want to point out, particularly at the beginning of every chapter where you get a lot of key terms and theorems and stuff, I'm never going to test you on like, hey, define the tangent line to circle theorem, okay? Or define chord, use diameter in a sentence or anything like that. This is not an English class. I'm not going to do that. I've never been a fan of like, hey, what is the name of this theorem? It comes in handy for abbreviating it, but what I'm going to care far more about is you know how to use it, okay, and understand what it is. And this is arguably one of the most critical theorems in regards to circles in general, but definitely the most important theorem when it comes to something that is tangent to a circle. All right, so formally, the definition says, tangent line to a circle theorem. A line is tangent to a circle if and only if, I'll come back to that phrase in a second, if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So that's a very dense definition. Part of the reason why I'm not going to expect you to memorize it and stuff. But here's the punchline of it. Here's what it's saying. If I tell you I have a tangent line, by definition, that means it's only going to touch the circle at exactly one spot. In this case, in this diagram, it's at point P. All right? So this line M is tangent to circle Q at point P. Touches only at that one spot. It's going to go off infinitely in both directions. At point P, line M is the one and only tangent line that can exist. Any other slope of line is not going to intersect at P anymore, or it's going to be secant through the circle and intersect at multiple spots. This is the one and only tangent line that exists at point P. What this theorem breaks down is that point P is on the circle. If I were to connect it to the center of that circle, I create what's called a radius, right? And we use the term a radius, implying that there are an infinite number of radii all around the circle. There would be any point, if I were to connect it to the center, it's another radius. This is just one of the radii. It will have the same exact measurement as all the other radii. But because line M intersects at this one point, there is exactly one radius that will connect to that point. This theorem says that those 2 unique things, the tangent line and the radius that connects to that tangent line, have to form a right angle. They have to be perpendicular to each other. And that's massive, okay? It may not seem massive because you're sitting in a Math 2 class in high school and it doesn't seem like super significant, but in the geometric world, okay, for something as common and significant as a circle, which is a very special, unique shape in and of itself, something that is tangent to it has this very critical measurement. And here's where we see that term perpendicular pop up again, which you have seen in multiple years, in multiple sections, in multiple chapters. This overlap results in this kind of unique situation. And this is going to be very important. And so let me come back to that phrase, if and only if. This is actually a logic phrase that basically says it works both directions. Here's what I mean. All right, we are told in this definition that a line is tangent to the circle if it creates a perpendicular angle to that radius. In other words, this line M is tangent to the circle if this radius makes a 90-degree angle with it. Okay? So basically, if I know that this is a 90-degree angle, that forces this line to be a tangent. But the reverse is also true. Let's say I only knew that this line touches this circle, and that now I have this radius. If I can somehow show that this is 90 degrees, that forces this line to then be a tangent. And we're actually going to come across this in the 2 examples we're going to do in the next clip. Okay? So that phrase if and only if means it works both directions. Whether I start with the fact that I know that's a 90-degree angle, that's going to force that line to be tangent to that radius. Or if I start with, okay, I just have these geometric objects that intersect, if I can show that that is then 90 degrees, or if I start with the fact that, hey, this is tangent, it's going to force that angle to be 90 degrees. It goes both ways. It's the flip sides of the same coin. All right, one more theorem. Again, the punchline there is that something that is tangent to a circle forms a 90-degree angle with that radius at that point. And our last theorem for this section and for this clip is what's called the external tangent congruence theorem. That's a very, very dense thing. Don't worry about having to memorize that. Just breaking it down by language. External means outside. Tangent means it's an object that touches the circle exactly once. Congruence means it's going to have the same measurement. Okay. This is basically what it says. It's going to be very unique. This is a far more strict set of parameters. Basically, you're going to see the diagram that you see here on your screen. I have some external point, like point S right here. And then from any external point, whether it's point S that you see here in this diagram, or if I had drawn something like way out here, some other point out this way, from any given external point, there are exactly 2 tangents that I could draw from there. One that goes through the top of the circle and one that goes through the bottom. As you see here, it creates this little wedge shape, right? So any external point, I can create 2 tangents, right? What this is saying is that if I were to say like, okay, let me take those 2 tangents and simply break it down to, all right, here's the external point. There's the point of tangency. Here's the external point. Here's the other point of tangency from that external point. I create 2 segments, this wedge shape, right? What this theorem says is that this is unique in that these 2 segments have to be congruent. All right? So let me break that down again. So there's point S there, but let's say I put a point out here. From that point out here, there will be some point of tangency over here at this top part of the circle. The distance from that external point to that spot would be the same from that point to the point of tangency on the bottom part of the circle. Okay, so if I knew that this was 17.6 miles, that would also have to be 17.6 miles. Okay, kind of a life application here. If I were to think of point S as like some satellite and the circle as, say, a cross-section of the globe, the Earth, the range of what it would be able to affect where someone would receive signal would be that tangent point right there and that tangent point right there. Obviously, no one on this side is going to get any signal from that satellite because it'd have to go through the Earth, right? And so this would be representative. It'd be the same distance on this one as it would be on that one. Okay, so I'll go ahead and stop this clip right here, and in the next clip, we'll cover the 3 examples in this section.